Welcome to my video on special matrices. This is the fifth video in my series on matrix math. In this video I want to look at some specific matrices that we call them special matrices because they have peculiar features. First would be the symmetric, skew-symmetric, upper triangular, lower triangular, diagonal, scalar, and unit or identity matrix. I want to give you examples of each of these and try to explain it in a little more detail. So our first is our symmetric matrices, and these basically tell us that the transpose, we had a video on this, is equal to the original matrices. So let's do an example just to illustrate this point. So what we want to do is A, which is equal to A transpose. Let's just generate a matrix here. 20, 60, 200, first row. 60, 10, 75 in the second column, 200, 75, and 30 in the third column. All right, so let's see the transpose of this. If we do that, these two would trade places. Rows and columns trade places. So this row would become this column. So it would be 20, 60, 200, so that's the same. This row, that column would become the second row. So 60, 60, 10, 75, yeah, that's the same. And then the third row would become the third column. And you can see that's 275 and 30, 275 and 30. So that is the transpose. That's a symmetric matrix. Now, a skew-symmetric matrix is slightly different. There it's equal to the negative. So let's look at an example of that. So B is going to be equal to 0, minus 1, 5, 1, 0, 2, just making this up, minus 5, minus 2, and 0. So in this case, we want to say that the transpose is equal to the negative, so really it's just across the diagonals where you'll see things move. And those are the opposite of each other in sign. So that is going to be where the elements, and you'll notice in this case the diagonals got to be 0 because that's the only way this can work out to be a skew-symmetric. So that's skew-symmetric. The transpose is equal to the negative of the original matrices. Now let's look at the next one, which is called the upper triangle matrices. So upper triangular matrices are square, keyword, square matrices that can have non-zero entries only on and above the main diagonal. Below the diagonal entries are 0. This is a definition. So now let's see, 1, 0, 2, 3. That's a square matrix. That's a 2 by 2. So that satisfies that. And non-zero entries only on or above the main diagonal. So that, yes. Below the diagonal, you have a 0. So that is a upper triangular matrix. Now let's look at a 3 by 3 example. 6, 0, 0, 5, 1, 0, 5, 2, and then 19. Let's see if that satisfies the definition. Okay, below the diagonal we have zeros, and then on or above the diagonal, that's the diagonal that way, we have all 0 or non-zero entries. So that is going to be an upper triangular matrix. The lower triangle matrices are square matrices that can have non-zero entries only on and below the main diagonal. Above the diagonal, the entries are 0. So it's very similar to what we just did, except things are just going to be flipped about the diagonal. Let's look at let's look at a 2 by 2 example. 1, 0, 3, 2. Does that satisfy the definition? There's our diagonal. And then that is a non-zero along the diagonal. and the lower triangle square matrix that can have non-zero entries only on or below the main diagonal, so that. So above the diagonal, it's 0. So that is a 2 by 2 lower triangular matrix. Now let's look at a 3 by 3. 2, 8, 7, 0, minus 2, 6, 0, 0, 8. Let's see what we have here. So here's our main diagonal, and all the entries below the diagonal are non-zero, or they can be 0 actually, but the main ones over here in the above the diagonal, those have to be 0. So that is a 3 by 3 lower triangular matrices. Now let's look at what's called a diagonal matrices. A diagonal matrices are square matrices that can have, once again we have square matrices can have non-zero entries only on the main diagonal. So only on the main diagonal. All entries off the diagonal must be 0. So we'll call this, actually all these vectors should be capitalized or bolded. So I'm just, oops, trying to make that a bold. They all should be bold. So let's do a 2, 0, 0, 0, minus 3, 0, 0, 0, 6. So if we've got a diagonal matrix, now there's the diagonal. Those are not 0. Can have non-zero enters only in the main diagonal. So there could be a 0 there. But the main thing is this upper triangular part and the lower triangular part has got to be 0. Only entries you can have really are along the main diagonal. That's why they call it a diagonal matrix. Now, if all the diagonal elements are equal, say to some constant c, we call S a scalar matrix. So let's see what a scalar matrix properties. It's the matrices A times the scalar matrix is equal to S times A, which is just equal to C times A. So let's do a simple example to illustrate this. So A times S, just make these up. We've got 1, 2, 3, 4. And then so the scalar matrix is 2, 2, 0, 0. And so only along the diagonal, and they've got to be equal. So in this case, 2 and 2, 2, 2, along the diagonal, and then off the diagonal, there's 0. So let's do the multiplication here. So when we do the multiplication, we're going to get 1, 3 times 2, 0, the upper element here. So that's just going to be a 2. And the second, we take the first row times the second column. That is just going to be a 0. Let's see, let's do this out here. Take that times that. 1 times 0, 0. 3 times 0 is going to be a 6. So we've got a 6 in this position. Now to do the second row times the first column, that's going to be 2 times 2 is 4, and then 0 times 4, so there's going to be a 2. No, probably 2 times 2 is 4. And then the final element is going to be this last bottom row times this column. 2 times 0 is 2, and then 2 times 4 is 8. Okay, so there's the product there of A times S. Now let's do S times A. 2, 0, 0, 2 times 1, 3, 2, 4. Now, let's do that the same manner that we do matrix multiplication. And we do have a video on this if anyone would like to see my video on matrix multiplication. Okay, so first we take the first row times the first column. 2 times 1 is 2, 0 times 2 is 0. First element is a 2. Now we take the first row, second column, so that's 3 times 2 is 6, 0 times 4, so that's going to be a 6. In the second row, or second column, Now, to do the bottom row here times the first column, 0 times 1 is 0, 2 times 2 is 4. So that element's going to be a 4. And then finally we finish this off with 0, 2 times 3, 4. So that's just going to be 2 times 4. That's going to be an 8. Okay, those are equal. Now let's see what C, if C was in this case equal to a 2, does CA, what does that equal? So that's 2 times 1, 3, 2, 4, and that is equal to 2, 6, 4, 8. Just taking the scalar C times this matrix A. So these are all equal. We didn't prove this identity, but we did verify it, at least with one case. Next, we want to look at another specific case here. We start with a scalar matrix. Remember, those are as a non-zero, all constant, all the same along the diagonal, except this case they're all going to be equal to 1. And this is called the unit matrix or the identity matrix. And you'll see this a lot. This turns out to be important. Some you'll see more than others. This one you will see. All right, so let's look at the case of 1, 2, 3, 4. There's our matrix A times the identity matrix of 1, 0, 0, 1. Just as we said, it's 1s along the main diagonal, 0 everywhere else. Let's multiply that out. So going through our multiplication procedure, 1, 3 times 1, 0 is just going to give us a 1. And then in this position over here, we've got 1, 3 times 0, 1. So that's going to be 3 times 1. And then taking the bottom row times the first column. 2 times 1 is 2. 4 times 0 is 0. So that's going to be a 2. And then the final multiplication here, the bottom row times this column, that is just going to be equal to a 4. So that is the result. And it's just 1, 2, 3, 4. That's our matrix, and it just reproduced itself. Now let's do it in the opposite order. Let's take the 1, 0, 0, 1 times 1, 2, 3, 4. Let's do this multiplication. Okay, taking the first row, first column, we are going to get 1 times 1 is 1 plus 0, so we're going to get a 1 there. And taking the first row times the second column, we get 1, we're going to get a 3. And then the bottom row times the first column, 1, 0, that is just going to be a 2. And then the final multiplication here is the bottom row times the second column, so that's just going to be a 4. Okay, so that is the same, and that is also equal to A. So we just did an example of this identity, of the identity matrix, and how it can be used to multiply times a vector, times a matrices, gives the matrices back. All right, well, I hope you got something out of this video and learned about some of these special matrices. If you did, give me a like, thumbs up, and subscribe to my channel. I want to thank you for watching.